Hey guys, welcome to my channel. Today we're going to discuss depth first search using a USACO solver problem. This one is called closing the form. So let me summarize the problem using a okay. So we're going to be given n nodes and m edges, okay? And each n represents a barn, and m you can think of as a road which connects barns. So in our sample input, it's simply 1, 2, 3, 4. Actually, I would like to call them 0, 1, 2, 3 just because it's easier to implement that way. That's what I did in the implementation. And it's the same thing, pretty much. We're given 0, 1 connected, 1, 2 connected, and 2, 3 connected. So what we have to do is check if the whole graph is connected. That just means that you can reach any node from any other node. For this problem, you can clearly see, at this moment, you can clearly see all the nodes are connected. However, the main goal of the problem is it wants you to see if you remove a particular, node, any node, if the graph is still connected, and it keeps doing that, keeps giving you queries. So here we're given 3, 4, 1, 2, or we could call them 2, 3, 0, 1. So let's see if we remove 2. The graph is no more connected because 0, 1 are separate parts and 3 is a separate part. Now, next it removes 3, then obviously it's connected because it's just 0, 0 and 1. And then we remove 0 as well, then it's just 1, which is connected all by itself. And all we have to do is say yes if it's connected and no if it's not connected. Pretty simple. So what we're going to use is depth first search in order to accomplish this task. Let me show you the code, and then I'll show you what the code actually does. So, I use ArrayList, 2D ArrayList to implement depth first search always, and we always maintain a visited array. So let me go through the problem, the whole thing. So I take input here, and then I initialize a bunch of variables. And you always, the point of adjacent here is that you keep track of the nodes that are adjacent to a particular node. For example, in the sample problem 0, 1, 2, 3, 1 is connected to both 0 and 2. So adjacent at index 1 would contain an array list that contains all the nodes that 1 is connected to, which in this case are 0 and 2. Similarly for all other indices. It would contain array lists that keep track of which indices it is connected to, which nodes it is connected to. So that's that, and that code basically implements that part. And we have a barns because this basically keeps 0, 1, 2, 3, 4 in no particular order. It's just there to keep track of the size of the current barn, which means like as we remove some of the barns, we have to keep track of the size, so we just use that array list. And then we have a visited. This is very important. I'll go on this later when I actually discuss the depth first search algorithm. And removed is only specific to this particular problem because you generally don't have a removed in a depth first search implementation. But since we are removing nodes, we have to keep track of which nodes we are removing. So I'm going to use a Boolean array to keep track of that. So as I said, inputs, some of initializations, and here is where the actual code comes up pretty short. We take the query, which is what element we are removing, and we always set the visited to a new Boolean array because we don't, as I said, we are doing a new depth first search each time we are removing a node. And we also set total equals 0. Total basically keeps track of how many elements are in a particular connected component, and that makes sense because if the whole graph is connected, the size of the length or the total value should be equal to the size of the whole barn. Here is where, as I said, the size of the barns comes into play. That's why I used an array list. And we're going to print s if it's equal and no if it's not. And we again remove the given query and also set the removed part equals true. So here is basically the code, which is pretty simple. As you can see, depth first search. So we always put the visited of that particular index to true, and then we increment total because that's one more element in the connected component. And then the final step, most important, is the recursive part. We look through all the adjacent elements to that particular index or particular node, and if that particular node is not visited already, and it's also not part of removed, and then we just depth first search that node too. So what this does, let me demonstrate on over here. So I always start at the 0th element because it doesn't matter. If the whole graph is connected, whatever point you start from, you should end up with all the points. So that's the ideology behind it. So I just chose arbitrarily the first point. In this case, that would be 0. So let's say when all of them are connected, 0, 1, 2, 3, I start at 0. Actually, let me show you what the ArrayList edge contains. It's basically ArrayList, 2D ArrayList. So at 0, it would contain 1, and at 1, it would contain 0 and 2, and at 2, it would contain 1, 3. At 3, it would contain 2. It makes sense, right? Because those are the things each of these is connected to. And when we start at this node, we increment the count because obviously the particular node is not visited, and then we go to 1. But since 0 is already visited, we won't take care of this, but we'll go to 2. And here 2 again we increment, but we already visited 1, so that, and we go to 3, and then 2 is already visited, so we do nothing. So that 4 is equal to the bound size, and that means the whole graph is connected, and we return true, yes. And when we remove the 2, this is how it looks. 0, 1. Actually, it will still contain 2, 3. That's why I have the removed array, which basically checks very quickly if we should go to a particular node. It contains the same elements basically. The only thing different is when we go to 1, it doesn't go to 2 because 2 is part of removed. So it doesn't go to 2 or 0. So we basically stop. However, the 2 is not equals to 3, which is the size of the bound. So we return false. But when we remove the 3 as well, 0, 1 are connected. So obviously we'll return yes. And again, when we remove 0, 1 is connected all by itself. And so we return yes again. So the 3 things I want you to take away from this video are, when you're using depth first search, it's pretty easy to implement it using the 2D ArrayList, as I just mentioned, like edge here. You just need to make sure you add it to both. You add the things to each other. Is simply put, and it's also important to have a visited array so you don't run into infinite recursion or whatever. And it's very smart to use a visited array instead of something like an ArrayList, because this runs in basically linear time. If you were to use not linear time, constant time, so it actually doesn't even depend on the size of the visited array. However, if you were to use something like a ArrayList integer or something to keep track of what you have visited, then it would take at least log n, because it has to search through its elements to get to that particular element. So that's why it's very useful, convenient to use visited. That's why I use 2 here, because this particular problem requires me to use 2. But generally you just need a visited array. You don't need a remove, because you don't really remove nodes when you do this sort of thing. So yeah, that's it for now. Please let me know if you have any questions about the first search or any other Silver algorithms in general. So see you next time.